Welcome to Impact Signals, social impact at the scale of AI. I'm Charlie.
And I'm Sarah.
It's Sunday, March 22nd, episode 37 of Impact Signals. Today, we're tracking an active disaster in Hawaii and 3 breakthroughs reshaping how AI serves the field. We start in Hawaii, where this weekend's flooding is being called the worst in over 20 years.
Major flash flooding hit Oahu beginning Friday, driven by Kona low winter storm systems, southwesterly winds that funnel warm, moisture-laden air into the islands. The National Weather Service had most of the state under a flood watch, with Haleiua and Waialua in northern Oahu under flash flood warnings. Emergency alerts told residents to leave now.
How bad did it get?
Over 200 people were rescued across the island. The National Guard and Honolulu Fire Department airlifted 72 people, including children from a spring break youth camp off Oahu's west coast. Both main roads into the affected zone flooded, cutting off ground access entirely for the first responders trying to get in.
And there was a dam concern.
Still is as of Saturday morning. The Wahiawa Reservoir Dam, 120 years old, 17 miles northwest of Honolulu, had water levels rising to within feet of the crest overnight. The island's emergency management department declared it at imminent risk of failure. Water receded Friday evening, then rose again overnight with more rain.
Governor Josh Green put the cost estimate at over $1 billion, including damage to airports, schools, roads, and a Maui hospital. Climate scientists are pointing to a documented increase in the intensity and frequency of Kona lows as global temperatures rise.
The practical takeaway for responders is a hard one. NOAA's flash flood warnings functioned correctly. The alerts fired. But when main evacuation roads are themselves flooded, algorithmic early warning hits its limit. The infrastructure gap, not the data gap, became the operational constraint.
That's the recurring theme in this work. The AI works, the roads don't hold. Let's move to 2 breakthrough research findings this week. Both address the same problem, flood forecasting where you have almost no historical data.
This is a genuine inflection point. 2 peer-reviewed studies published this week confirm that AI foundation models, systems that generalize patterns across enormous cross-domain datasets, can forecast river flows in data-scarce regions with accuracy comparable to models trained on decades of local records.
Walk us through what that means practically.
Right now, early warning systems for floods in most of the global south are limited or non-existent because they require long historical gauge records. River monitoring equipment costs over $1 million per station. Much of Africa, South Asia, and the Pacific Islands have a fraction of the coverage that Europe or North America does. The conventional assumption was you can't forecast what you haven't observed.
And the new studies break that assumption.
Yes. Researchers at the University of Texas at Austin, publishing in the journal Machine Learning Earth, tested a foundation model called Sundial across more than 500 river basins. No basin-specific data training. The model performed comparable to systems trained on decades of local records. A parallel study from University of Minnesota showed that knowledge-guided machine learning outperforms the National Weather Service's current physics-based models. And critically, it eliminates the manual field recalibration that forecasters currently have to perform in real time during weather emergencies.
That's the operational piece. It's not just more accurate, it's less labor-intensive at exactly the moment you need it most.
Nature published a companion piece this week, a caution flag. It calls for more rigorous testing before AI forecasting approaches are widely adopted by national agencies. The specific concern? AI models can perform well on average, but underperform on the extreme tail events that constitute actual humanitarian emergencies. The field has to distinguish between average accuracy and worst-case performance.
The money context here matters. Swiss Re is projecting insured catastrophe losses of $148 billion in 2026. That would be the 6th consecutive year above $100 billion. The private sector is not waiting for standards to settle. They're deploying AI risk tools at speed. The humanitarian sector has to move faster.
Our third story is a partnership that directly addresses early warning latency. Planet Labs, which operates one of the largest commercial satellite constellations, announced this week that it's integrating NVIDIA GPUs directly into its next-generation Pelican and Owl satellites.
What does that mean in practice?
Today, satellite imagery goes through a sequence: capture, download to a ground station, upload, then AI processing. That sequence typically takes hours. The new architecture moves the AI processing on board into orbit. Planet's Owl constellation, designed specifically for disaster relief and emergency response, would deliver high-resolution imagery that has already been AI analyzed before it reaches the ground. The target? From image capture to actionable intelligence in under 1 hour.
That's a significant compression.
For field teams doing damage assessment after a cyclone or earthquake, that's the difference between deploying in the first response window and arriving with yesterday's data. The tip and cue workflow means the satellites can automatically flag anomalies, structural collapse signatures, unusual displacement patterns, nightlight changes, without a human analyst manually reviewing every frame.
We close with a story from Kazakhstan that should be on every social protection practitioner's radar. UNICEF, working with Kazakhstan's Ministry of AI and Digital Development and Ministry of Labor, applied something called causal machine learning to the country's household cash transfer program.
This is different from what most people think of as AI in social programs. Standard machine learning predicts outcomes. Causal machine learning asks, for whom does this intervention actually change outcomes, and by how much?
What did they find?
They applied the method to 600,000 households. The average impact of the cash transfer program looked small, unremarkable. But when the causal model looked at subgroups, it found the most acutely vulnerable households received 2 to 3 times the average benefit. The average was masking a highly unequal distribution of impact.
So the program was working, just not for everyone equally.
Exactly. And the government is now preparing to use that insight to scale the program to 6 million households nationally, targeting resources toward the households where they change outcomes the most. What makes this practically replicable is that the method doesn't require clean, pre-curated data. The algorithm itself helped identify and fix data gaps as it ran.
For organizations running anticipatory cash programs after disasters, and that includes WFP, UNHCR, Give Directly, this is a methodological template. Not just did the cash help on average, but which household should receive it first to maximize impact per dollar.
The urgency is real. The UN estimates 305 million people will require urgent humanitarian assistance this year. Funding coverage has dropped from over 60% in 2011 to 43% in 2024. Getting more out of every dollar deployed is not a nice to have.
Before we close, a few events worth noting. The AAI Spring Symposium on AI and Humanitarian Disaster Response runs April 7th through 9th near San Francisco. That's the key academic practitioner bridge event for the field this quarter. RightsCon, which covers AI governance and digital rights, is in Nairobi from March 28th to 30th. And the Action on Disaster Relief Conference is in Washington, D.C., April 8th through 10th. Practitioner heavy, worth attending if you're in the space. That's Impact Signals for Sunday, March 22nd, 2026. If this briefing is useful, subscribe wherever you get your podcasts. Check us out at impactsignals.ai and share it with someone working in the field.
Stay ready.